हेलो स्टूडेंट्स। टिल डेट हमने जो प्रॉपर्टीज हमने जो ग्रुप में स्टडी किया, एब्लियन ग्रुप, सेमी ग्रुप, ग्रुपॉइड, मोनोइड। अब उसके उस उन जो हमने स्टडी किया उस चीज को जनरलाइज करते हैं। अलजेब्रिक हमें ग्रुप दिया होगा। ग्रुप मीन्स ऑल द फोर एग्जाम्स होल्ड ट्रू, मीन्स क्लोजर, एसोसिएटिव, existence of identity element and inverse element exist in G. This is the binary composition. The concept of binary composition is clear to you till date. Now we'll discuss the elementary properties of group. So the first property is the identity element of a group is unique. So we prove the uniqueness of the identity element of a group. So we'll prove it by contradiction. Contradiction means, let us suppose that E and E dash be any two identity elements of G group with a binary composition defined on this way. This moment is it. Now E and E dash are identity elements. So first let us suppose that E is the identity element. E is the identity element. We have two identity elements. Let E is the identity element. So if E is the identity element, then E dash is any element of G. So if E is identity, then E composition with E dash is equal to E dash is also equal to E dash composition with E for solution. Now, if we suppose that E dash is the identity element of G, E dash is the identity element of G, then E will be the any other element of G. So E dash composition with E is equal to E because E is the identity element is equal to E composition with. Now the first and second implies E composition with E dash is equal to E composition with E dash composition with E. So this implies this this is equal to this and this is equal to this. E composition with E dash is equal to E composition with E dash, and E dash composition with E is equal to E dash composition with E. That equal this equal to this. This equal to this implies E dash is equal to E. First and second implies E dash to E. If this implies if any group has an identity element, that we have supposed that there are two, but we concluded that we have proved that if identity element in a group exists, that will always be unique. Now next is inverse of each element in a group is unique. Inverse of each element in a group is unique. Again, we'll prove it by contradiction. Let G is a non-negative set with binary composition this O is a group. Now, if this is a group, then we have group means all the four exams hold true: closure, associative, additive exists, and immersive exists. So let us suppose that E belongs to G is the identity element of G. Now, if for all A belongs to G, all the elements of G, B, let us suppose that it has two inverse elements, B1 and B2. Now, A for all A belongs to G, two inverse elements. If B1 is the inverse of A, then we know that inverse of each element exists in G. A composition with B1 is equal to E is equal to B1 composition with A first equation. Similarly, if B2 is the inverse of A, then A composition with B2 is equal to E is equal to B2 composition with A. Then first and second imply A composition with B1 is equal to B1 composition with E. They are equal. They are equal. So now, in order to prove this, let us take we can take B1 here or B2 here. So now let's take B1 is equal to B1 can be written as B1 composition with E. You know, is because E is the identity of G. So now we have taken B1 here, so we'll substitute the value of conveniently we'll substitute the value of E conveniently, so that is equal to from equation B1 the first equation, so we'll substitute the value from the second equation. A composition with, we'll make use of these two equations. So B1 composition with A composition with B2. Now associative law holds true because G is a group. Therefore, B1 composition with A composition with B2. So B1 composition with A, B1 composition with A is equal to E. Substitute the value here. So E is the identity element. E composition with B2 is equal to B2. So this implies B1 is equal to B2. We suppose that for each element of A, we have two inverse elements in group G, but they comes out to the same. Implies if inverse element of any element in the group exists, that is always unique. Next is if G with this binary composition, if G is this with this binary composition is a group and A belongs to G, then we have to prove inverse of A is equal to. Now G is a group. If G is a group, and let us suppose that E is the identity element. Now for all A belongs to G, because G is a group, then inverse of each element exists in G. So this also belongs to G. Inverse also belongs to G. Then if A for all A belongs to G, inverse belongs to G, then A composition with A composition with A inverse is equal to A composition with A is equal to B. Then we say that inverse of A is inverse of A is A inverse, and inverse of A inverse is A. So from this we conclude that inverse of A inverse is equal to A. Can prove here also. We have taken the left hand side of there. A inverse is equal to A inverse into E. Composition with E. Now substituting the value of A here. A is equal to A inverse is equal to composition E. Substitute the value of E from equation first. Now associative law holds true here. So this can be written as A inverse composition with A inverse is equal to A. A belongs to G, A inverse belongs to G, A inverse also belongs to A, inverse of A also belongs to G. So A inverse into A inverse of A is also equal to E. So substituting value here equal to E here. If A belongs to G, A inverse belongs to G, A inverse belongs to G. Inverse of because G is a group, inverse of each element is. So substituting here. So E into A is equal to A. So this implies inverse of element is element itself. So inverse of each element, if G is a group, then inverse of each element of G is also element of G. Reversal law of inverse of product in a group G, that is for all A belongs to G, A composition B inverse is equal to B inverse composition with A inverse. So proof for this is, since A and B belongs to G, given G is a group, therefore closure property holds true. A composition B also belongs to G because G is a group. Let's suppose this is equal to C. Equal to A composition B is equal to C. Also, B and A belong to G implies G is a group. So B inverse and A inverse belong to G. So G is a group. Closure property holds true. So A inverse and B inverse composition with A inverse also belong to G. So let us put this. Now consider C composition D is equal to A comes with P, comes with T. Associative law holds true. Associative holds true. Therefore, A composition with B composition with T. Substitute value T here. T is equal to A composition with B composition with B inverse composition with A inverse. Again, associative law apply here. So A composition with B composition with B inverse composition with B composition with B inverse is equal to E, because B is equal to G and G is equal to E. E composition with A inverse is equal to A inverse. So we are left with A composition with A inverse, with A is the element of G is a group, therefore A composition with A inverse is equal to E. So this implies C composition with D is equal to E. Similarly, we can prove D composition with C is equal to E. Similarly means D substitutability here, D and D here, C here, D, then apply the same associative law holds true, and you can prove it. Then third and fourth implies D composition C is equal to C comma D is equal to E. Again, interpretation this is inverse of C is D, or inverse of D is C. Inverse of C vector is D vector. Inverse of C, inverse of C is D, and inverse of C is D, and inverse of D is C. C inverse. Inverse of C is D inverse, and inverse of D inverse D is C inverse. So that is, what is this? What is this? This is C inverse equal to D. C inverse is equal to inverse of C is D. D inverse. Inverse of C is D, and inverse of D is C. Inverse of C is D. Inverse of C is D. So this is equal to this. Substitute the value here. C, value of C, and D here. So C inverse is equal to D. So reversal law, reversal law of product. It was true in matrices. It was true in this adjoint of matrix, and in some other cases also. Reversal law. Reversal of inverse also holds true in the case of both sides. Cancellation law holds true in it. That's it. That is, for all ABC belongs to G, then if A comes to B is equal to A comes to C, then we have to prove that B is equal to C. This is called depth cancellation law. Second is, if B composition with A is equal to C composition with A, implies we have to prove that B is equal to C. This is called right cancellation law. So let's prove it. First cancellation law, let A, B, C belong to G is given, and G is a group. Therefore, if G is a group, then inverse of each element exists in G. Since G A belongs to G, therefore A inverse belongs to G, such that A inverse into A is equal to E is equal to A into A comes with inverse. E is that element of G, G is a group, inverse of each element exists, and this relation proves true. Given A composition with B is equal to A comes to C for all ABC belong to G, ABC belong to G. Now to prove is B is equal to C. Now using depth cancellation law with respect to A inverse on equation 7 in this equation. So A inverse composition with A composition with B is equal to A inverse composition with A inverse C. Now apply associative law. A inverse composition with A composition with B is equal to A inverse composition with A composition with C. So A is the inverse of A, so therefore A inverse composition with A is equal to E. A is the inverse of of A. A is the inverse of A. Therefore, A inverse composition with A is equal to E. E is the identity element, so E composition with B is equal to E composition. E is identity element, E composition with C. So this will be E equal to C implies the result. That means left cancellation law holds true. Similarly, you can prove for the right cancellation law. Right cancellation law means you have to apply here. You have to apply here right cancellation. Your right cancellation from here. You have to multiply here using left cancellation with this to this. Now we'll apply right cancellation with this to only then we can prove the right cancellation. Cancellation law also holds true in a group. So new note of the difference here. If A and B be any elements of G, then the equation A comes with X is equal to B and Y comes with B is equal to B have unique solutions in G. We'll prove first so equation. We'll find that we'll show that this equation solution of this equation exists and that is unique. Similarly, you can show for the solution of this equation exists and that. So I'll show it for the this equation A comes with X is equal to B. Since G is a group and A belongs to G, therefore A belongs to B because G is a group. Such that A comes with A inverse is equal to A inverse comes with A is equal to. Now that's the first equation. Since A inverse belongs to G and B also belongs to G, so G is a group, closed group is holds true. So A inverse comes with B is equal to what belongs to G, which is equal to true. Let us suppose this is equal to X. This is equal to X for the we have supposed this X for the equation A equals X. In the case of if you want to solve Y equals to A is equal to B, you have to suppose in the way B inverse B belongs to G, B inverse belongs to G, so B inverse into A, B inverse into B inverse comes with A is equal to suppose is equal to Y and equal to. Now take X is equal to this. Now this implies we now will prove that the solution of this equation A composition with X is equal to B. The solution of this equation exists. Then we'll show that the solution is unique. Now we'll show that equation second is this is the solution of equation A composition with X is equal to B. Now we're taking the left side of this. A composition with X, A composition with X. Substitute the value of X here. X. So suitably we'll write this suitably this value of X. So substitute value of X. A composition with A inverse composition B is equal to associative law here. A composition A inverse is composition B because A is element of G, G is a group, therefore A composition A inverse is equal to E. E composition with B is a identity element, therefore is equal to B. So this implies A composition with X is equal to B. And therefore the equation A composition with X is equal to B having solution. Now we'll show that this solution is unique. The solution of this equation is unique. So again, proof by contradiction. Let us prove that this equation have two solutions, x1 and x2. Two solutions. So if they are x1 and x2 are solution of this equation means both the solutions satisfy the equation. Replace x by x1. This holds true. X by x2. This holds true. So we got fourth and fifth equation here. Now right hand side both equations same. The left must be equal. Left is equal. So now apply left cancellation law with this to A inverse on equation 6. So A inverse composition with A composition with x1 is equal to A inverse composition with A composition with x2. Now apply associative law here. A inverse composition with A composition with x1 is equal to A inverse composition with A composition with x2. So A inverse composition with A is equal to E. E composition with x1 is equal to x1. A inverse composition with A is equal to E. E composition with x2 is equal to x2 implies x2. We suppose that this equation has no solution, but come to the conclusion that both the solutions are equal. Hence this equation A complete X is equal to B have a unique solution in G. Similarly, you can prove for the equation Y complete is equal to B have a solution of this equation exists and that is unique. Now next element property is prove that the left cancellation and right cancellation are the same. Left identity and right identity are the same in the group. Again, let us prove that Let us know that E1, E and E dash be the left and right identity elements of the group G. This group G with verification is circle. Then first is if E dash belongs to G and E is its left identity element, then left identity E composition with E belongs to E composition with E dash is equal to E. First equation. Similarly, if E belongs to G and E dash is the right identity element, then E composition E dash is equal to E dash is equal to E. The first and second equation, first and second left hand side of both equations are same. Therefore, first and second are same. Therefore, E is equal to E dash. Hence, left and right identity element of a group are is same. Both elements same. If it is unique, then it means that they are same. Similarly, left and right inverse of every element in the group is same. Okay, we prove it. Let E is the because G is the group, E is the identity element of the group. G is and B and C are left and right inverse of the element A of G. This is B is the left inverse of A and C is the right inverse of A. That means so if B is the left inverse of A, then B composition A is equal to E. If C is the right inverse of A, then A composition C is equal to E. Now first and second equation they equal. Again note to this. Now B can recognize because E is the identity element of G, so B composition with E. We can add B. This is again equal to B. Now substitute the value. We have B here. Now substitute the value from A is third. B is here. So you put another equation. Yes. Now similarly A composition with B and B composition with A composition with C. As Shankar holds true. So B composition with A composition with C. B composition from first equation. B composition A is equal to E. E composition C is equal to C because it is a identity element. So this comes E is equal to C implies we suppose that the left inverse and right inverse are different, but they come out the same. Implies left and right inverse of each element in a group are same. Thank you very much.